to attend this webinar. So I am Rick Malik. I'm a lecturer at the University of Glasgow, and I'll be presenting some of the underwater ocean acoustics research that I've been doing at Glasgow for the last couple of years, and also for a few months before that at my previous appointment. So the title says it's computation modeling, and there's also a bit of experiments, but probably for today, I'll be only focusing on the computational modeling and development of AI/ML-based models with a short note on what experimental research I'm involved in this area. Okay, so about myself, I'm a lecturer in aerospace engineering. However, underwater ocean acoustics and underwater acoustics in general has been of quite, I've found it quite fascinating area of research, and I've been involved in broad and multidisciplinary research in this field for the last 2 to 3 years. My PhD was from Virginia Tech in the USA, and then I've been to a few places as postdoc appointments, the latest being at a fellowship at the University of British Columbia, where I got introduced to this sort of fascinating area of underwater acoustics. My research interest, though, is quite diverse, and I work on aero and hydrodynamics, aero and hydroacoustics, and also application of AI/ML models for learning complex fluid flows. I have collaborators across a wide range of institutes, both in academia as well as across this UK government, and also institutes like University of British Columbia and Indian Institute of Delhi. They're broad partners, but my more, I would say, in-house or local collaboration is with the University of Strathclyde in Glasgow, and with the Manufacturing Institute of Scotland. Okay, so a bit of overview of what I will be presenting today. So most of it is going to be computational analysis of underwater acoustics, where I'll talk on development of high-fidelity computational modeling approaches, both for, let's say, deep water wave propagation modeling in general, and also on specifically for underwater ocean acoustic. And then I'll also discuss some of the research on novel AI/ML-based modeling. Again, it has two different aspects to it. One is long-range underwater acoustic transmission, and the other part is looking at temporal evolution of acoustic scattering and interference. Regarding the underwater noise testing, I would have liked to present something today, but it's still sort of research that's going on. What we do is we work on, we're really interested in acoustic scattering and backscattering from underwater, let's say, non-uniform underwater surfaces, and we develop creative testing concepts to study some of those experimentally. Okay, so a bit of, before we go into all the details of the research, I just wanted to share the motivation which has driven my research for the last 2 or 3 years. So underwater radiated noise has increased globally over the recent years, and noise pollution is an issue across the world. If you look at for example, the chart over here, let's say, this shows global noise levels from marine traffic. On the right, we have this increase in underwater noise intensities in the Arctic Ocean in the last decade, and it shows it has almost doubled in the last decade. So if we think about it, why are we interested in this? It's important because URN acts as a stressor to marine mammals. Let's say if we want to visualize this, let's say we have a ship traveling near the water surface, and then it creates this sort of underwater acoustic waves, which then affects various natural activities regarding, reproduction, or even food and other communication of this underwater mammals. And this is a concern for us So we need to have some sort of fast and accurate prediction capacity for URN to ensure that all the industrial activities in the ocean are environmentally friendly. Now, the near background on underwater acoustics is twofold. One is near field noise generation and characterization, and so that we have a better understanding of where these noise sources are or what these are and how they behave. And this is a highly nonlinear and multiphysics, multi-scale problem. As you can see here, it's evident here, let's say, if you're looking at, for example, offshore wind turbines, the pressure waves from this wind turbine mast can act as underwater noise source, which are quite complicated to analyze and characterize. Similarly, if we have marine vessels on the ocean, they have different sources of noise. It could be due to propeller creating. You have structural vibrations, then there's vortex shedding from the propellers, and we could also have things like cavitation. All of these lead to a very complex broadband noise source. So this is a nonlinear multiphysics, requires nonlinear multiphysics analysis, and that is one aspect of underwater noise. But this is my focus is more on the far field noise radiation, which can also be a nonlinear multiphysics and multi-scale problem. It's evident again here, for example, what I'm showing here on the left is the transmission loss due to geometric spreading and attenuation obtained from, let's say, even single monopole sources. And you can see that this can lead to very complex acoustic signals and acoustic wave traces in the ocean domain. On the right, I'm just showing you the effects of acoustic scattering, which is often three-dimensional and requires and leads to highly challenging modeling and computational analysis. So that's the motivation. This is where my research is focused on, the far field noise radiation. To begin with, the question is how should we model ocean acoustic, right? So a bit of understanding of the present practice is required. So what we have at present, we just model underwater noise radiation as, let's say, a wave propagation phenomena, right? And then computing URN essentially becomes solving the sort of two linear second order PDE for pressure fluctuations as we have here. And we know techniques how we can solve them both in time domain, or we can simply convert them into frequency domain and solve for these equations. So essentially what we're saying is that if we have some sort of sound wave, it leads to outward motion of these acoustic waves. At present, the routine methods are mostly based on hybrid analytical and numerical methods. For example, Gaussian ray or beam tracing, where essentially we use ray tracing to see how acoustic waves are propagating underwater, right? And this is a frequency domain analysis. And schematically, we can think of this as, let's say we have this type of ocean domain, right? So this is a very highly idealized two-dimensional section of an ocean. And we are saying that this is the depth and range with reasonable representational values. Ranges usually are, or at least ranges of importance are usually in the orders of kilometers, depth being about 1,000 meters at most. And we would have this type of variation in sound speed in the water. This is well-known Mach's speed profile of sound in the water. And the ray tracing essentially uses this technique that, let's say we have this as a source at 1,000 meters of depth, let's say, and then we will just throw out an array of rays over a large angle, right? And then these rays will be following Snell's law essentially when they're going through ocean depths with varying sound speed, and they will eventually span the entire domain. And by summing a superposition of these ray amplitudes, we can calculate what, for example, is the acoustic pressure at some point, let's say, at some point in the domain. The acoustic pressure and compare them with our source pressure, and we can get an estimation or some sort of estimation of the transmission loss in decibels of the sound of the acoustic pressure, right? And this takes into account things like geometric spreading and interference from different surfaces. So that is the state of the art that we have at this point. Now, there are some challenges and limitations with this type of numerical ray tracing. First is that we are limited to very simple sound sources. Essentially, what we are saying is that we have a very simple point source of single frequency, and that is leading to this type of acoustic, let's say, pressure distribution in the ocean domain. And we cannot really use distributed boundary conditions. So the boundary conditions that we can use with this type of ray tracing or using this type of principle of superposition is limited. And then there are things like shadow zones, which is often a limitation. It's an artifact of how ray tracing is used. For example, what we are saying is we have set out a range of rays, and these rays are being traced, are then propagating throughout the domain. But there could be regions where no rays actually would enter. And then there's no way for us to know what is happening at those regions because there's no ray traced at those points. And these are the shadow zones, for example, shown in red over here, which sort of shows zero acoustic pressure, but it may not be the reality. So these are some of the limitations that we have for numerical ray tracing, which led to, which was sort of the motivation for me to develop this sort of modeling techniques for computational underwater acoustic. And what I am doing here is using open source software. We are numerically solving the acoustic perturbation equations. So these acoustic perturbation equations are obtained from for fluid mechanics, but provided that we apply the conditions of small perturbations and also incompressibility in the ocean, we can eventually obtain the linearized and the lack of viscosity for wave propagation. We can obtain the linearized Euler equation, and then if we filter out some of the hydrodynamic sources in this linearized Euler equations and get rid of any source of hydrodynamic instability, we will end up with this acoustic perturbation equation where the sources on the right-hand side are really filtered out sources which only can excite the acoustic behavior in the equation, right? So that's the essence of why we are even solving this acoustic perturbation equations, but this would be sufficient improvement in, or at least increase in fidelity compared to the ray tracing technique that we have. So with this type of method, it's a general numerical equations solving approach, and we can use high order spectral elements to solve any given problem with complex range and depth dependent ocean properties. For example, let's say we have this type of non-uniform ocean bathymetry and highly complex changes in both ocean sound speed and water density in the ocean. So we can solve many of those arbitrarily complex problems. And then we can also directly solve for complex broadband sources. For example, actual sources from the fluids can be coupled with the acoustic solver, and we can solve for these problems. So what we can say that is this source vector shown over here can be any arbitrary function of the spatial domain and frequency. And the frequency range could be broadband, starting from 10 to 10 to the power 4 hertz. There are some challenges as well with this type of approach, especially the computation time. The ocean length scales can be very large, hundreds of kilometers, and the high frequency acoustic sources can be a challenge, but we'll come to that later. So to begin with, I'm going to show you some of the cases that we have already studied with this numerical solver for acoustic perturbation equation. We have looked at, let's say, this type of general scenario where we're mainly focused on acoustic scattering analysis from rigid surfaces and mixed boundary conditions and dispersive broadband sound sources. So let's assume that the ocean domain here is slightly more realistic than the very idealized situation we had earlier. Let's say this is the black picture. This represents a reflecting sort of solid seamount in the ocean. And then we can have a combination of lossy ocean bed, which lets in, which can absorb sound. We have a reflecting ocean surface, which fully reflects any acoustic waves from it. And then we can have far field surfaces, which sort of behave as which absorbs noise and behaves as numerically as a far field boundary condition. So if we have, so we can have, again, some arbitrary location of sound sources, and we want to see, let's say, how these sources are being backscattered or scattered away from various different bathymetry or various different seamount shapes, right? So that would give us a good understanding of the acoustic scattering here. So I've presented here a couple of cases where this can be, let's say, considered as seamount shape 1, and the other one is seamount shape 2, and you can see that we are looking at quite complex scattering of sound waves, of acoustic waves, and the two cases are completely different frequencies. The one on the left is quite a low frequency. One on the right is quite a larger frequency. But we can see already the highly complex interference patterns due to this type of backscattering from the oceans, from the seamounts. Right? So these snapshots were sampled at 200 hertz, and some of these simulations took around 12 CPU hours. So it's significant, but not very large, at least at this point. And keep in mind that we are only looking at about 100 kilometer, about 1 kilometer only in range. So this CPU hours will scale up pretty quickly. But we have been able to explore the physics of acoustic scattering quite well. A bit of details on how we were developing the mesh here. These are all P4 elements with 16-noded quadrilateral elements. The nice thing about acoustics is that we can have uniform mesh size, and the only thing that actually dictates the mesh size is the smallest wavelength of acoustic signal. And we can, once we know that what's the mesh required to proper sampling of the wavelength, we can just use the same mesh throughout the domain. So what we also wanted to do was to do some sort of numerical convergence study, that whether we were able to sample all these solutions, all these scattering effects, they were sampled accurately. So what we did was, let's say that blue one is a source, and we placed a receiver over here shown in yellow, and we looked at various different mesh size orders of our finite element, orders of the finite element shape functions, and also the different sampling frequencies. And this shows that what we have been using are quite accurate, and the results are quite converged, which again supports that the computational modeling is able to capture the acoustic scattering so far. And some of these results are available on this article over here in Physics of Fluids, and you can definitely take a look for further information. What we also wanted to scale this up to more realistic situations. And at this point, I want to introduce you to this, to the Dickens seamount. So what I'm going to do here is I will take a look. So this is the Dickens seamount here shown with this highly small blue dot. So I am showing you the west of Vancouver, where we actually have this seamount. So this is actually the Dickens seamount. So it's actually sort of cylindrical seamount, and it has of the west coast of Vancouver, and it has been, and I have selected this one specifically because it has been subject of various experiments and analysis in the past. So this is a well-known sort of case study here, and I've just used this one to for testing my models. So we have this case, let's take in seamount. Let's say it's a highly reflecting seamount, so it's sort of a fully reflective surface. The ocean surface is again fully reflecting. Ocean bed here, I have sort of artificially considered part of it as a lossy ocean bed and part of it as a reflecting ocean bed. And then we have this simulation here. So you can see that the waves get scattered by the seamount and from the surface, and then they form quite complex interference patterns because of this reflections and scattering effect. This one, as I said, was much more computational expensive case. It took around 80 CPU hours to complete. So this is, as I said earlier, the computation time will scale up quite quickly. Even we're not even looking at the full ocean domain, we're only looking at around 5 kilometers of range here. So what we also wanted to do was actually at some point go back and compare what we are able to get with the high fidelity simulations with what we can obtain from numerical ray tracing, and compare the two just to see how they look. So on the left, what I have is the distribution of transmission loss of the signal throughout the domain. And on the right, I have the similar analysis, but performed using numerical ray tracing, right? So what you can see here is that we have this patterns of relatively higher, lower transmission loss or higher acoustic pressures, which can be observed in both these solvers, which shows that the numerical model is able to predict the same sort of acoustic waveforms as, for example, the numerical ray tracing. However, it's important to note here that here we have this, let's say, highly dark regions, which shows that these are the shadow zones. It indicates that there's no rays that have been traced in this region, and there's nothing that we can predict about these places using ray tracing. That those regions with the spectral element method are less extreme, and it's just because we don't use the ray tracing here, but solve the acoustic. But numerical is solved throughout the domain for the acoustic perturbation. So this clearly shows that some of those limitations of ray tracing has already been solved using this type of acoustic perturbation equations. But otherwise, both the methods show good similarity in terms of the broad physics of acoustic, underwater acoustic propagation. So we thought, okay, why not try another case where we're looking at, let's say, the coastal bathymetry and underwater acoustics due to, let's say, multiple sources. This was, again, took around 80 CPU hours, but you can see how the waves from two different sources with quite different frequencies, and both of them being broadband, can lead to highly complex interference patterns, although they're slightly less complex looking compared to the previous case. And then we also looked at the same way we looked at the transmission loss of the signal, and we can see this highly complex wave patterns over the whole domain, right? And then we placed a few different receivers to see how much can we retrieve back about the signal, about the broadband, about the bandwidth of, let's say, of the response at these three locations. And interestingly, for receiver 1, we were able to locate all the 4 main frequencies which were used for exciting the sources. As you can see here, these are the 4 main frequencies that were used, and we could get, doing a 50 of the power spectrum, we could retrieve them back. things got a little more complicated when we were looking at the other two locations. For example, at receiver 2, we were not able to retrieve the very high frequency spectrum from the sampled data. This was, however, there in the receiver 3. So this could be indicative that that because of the highly complex interference patterns, there could be a significant loss of the power spectrum of the high frequency, and this is not as a result of geometric spreading, so it's not proportional to the distance, but it's just because of the destructive interference patterns observed at that region. So this shows that, and this is again indicative of highly complex and multi-scale nature of the underwater acoustic scattering that we are studying here, right? So, but to conclude this part of the talk, what I've demonstrated is that we are well into the development of a high fidelity computational modeling approach. This has been working well so far compared to existing numerical approaches like ray tracing, and we have been able to also address some of the limitations of ray tracing techniques. However, the computation cost can be a factor, especially if we scale up to real ocean domain size and parameter space. Which then brings me to the other aspect of my research, which is data-driven learning of underwater ocean acoustics. So the motivation behind this is that, for example, some of these issues like scalability could be a huge factor. So instead of only relying on high fidelity simulations, why don't we try to develop some sort of unifying data-driven model which can bring in data from experiments, high fidelity simulations, or even hybrid analytical models, and then we can also include some sort of physical priors to this data-driven model, and then that can act as a digital twin of complex acoustic propagation physics. So some of the issues are regular issues with this data-driven model are accuracy, how generalized are our prediction outside the training range, scalability, how much can we really reduce the dimension reduction, and also reduction in the computation time and interpretability. What does some of these results even mean, or how are they even working? How are the data-driven models even working? And that's something that's often not very clear. Here we'll only focus on the generalized prediction aspects for this presentation. And the method that we have proposed and used for the last 2 to 3 years is called a convolutional autoencoder network. It's sort of short acronym CRAN. Essentially, it's a composition of convolutional autoencoders and various type of recurrent neural network. And I'll be briefly noting on how we include physical priors with this type of neural network architectures. So very brief overview of autoencoders. I'll not go into the mathematical details. Essentially, what we're doing is we have this high dimensional data. We are encoding it and sort of encoding and compressing it into a much smaller dimensional latent state, and then the decoder then sort of expands this compressed latent data back into the high dimensional physical states. That's what the autoencoder does. And the recurrent neural network, what its main role is to form sequence-to-sequence prediction. Usually, we want to form this on low dimensional states. So let's say you have this input sequence. Let's say a few snapshots of your acoustic propagation. You feed that to the recurrent neural network, which in our case is a LSTM network, and it can predict you the next sequence of data, right? So if you provide a sequence of data, it will provide you the next sequence. That's what the LSTM is doing here. This can be explained mathematically. I'll not go into the details, mathematical details. These are available in various literature. What we also sometimes do is use some information that's available for system identification in the broad dynamical systems literature, and you make use of things like Taken's embedding theorem and use it to alter the way that we train some of these networks, and that acts as a physical priors to some of these black box type of techniques. This is in short a sort of a schematic, very general schematic of what this method works. Let's say we have this very simple, any general wave propagation or any signal propagation. Let's say these are the actual high dimensional snapshot of data. We feed this to this encoder via its various mechanisms. It will generate a very low dimensional data coming out from this actual signals in physical space. The LSTM will then propagate this data and give us the next set of latent states, next sequence of latent states. And then the decoder then expand this set of evolved latent states back to the high dimensional data, except that these are now the next sequence of propagated signals, right? So this is the input and this is the output in higher dimensions. That's how the CRAN network is working here. And there have been two ways that I've used it. I'm calling this the first case, I'm calling it as scenario 1 for application of CRAN. But essentially what I'm doing here is I want to use this CRAN for predicting the propagation of underwater, let's say, acoustic loss or transmission loss of underwater acoustics along the spatial dimension, right? So the idea is that we'll train it in such a way that given this initial bit of near field data, it can produce a small snippet of, let's say, the distance along the x-axis, along the range. And this process will be repeated over and over again until recursively we can add up the various predictions, fed autoregressively, and we can get this whole predicted distribution of transmission loss over the domain. So by running it over several iterations, we can predict the whole domain acoustic transmission loss starting from this initial near field information. So that's the scenario 1 for the application of the CRAN for underwater acoustics, and this has resulted in quite successful predictions. What we did was we looked at various different source depths and trained the network on a range of, let's say, a set of training data of the whole domain acoustic transmission loss. And then we tested it for a couple of cases outside the training range, and this is what we could obtain. So we fed this for two different out of training cases. We fed the near field transmission loss data, and these were the predicted results for those two cases, which you can see are structurally quite similar to the ground truth. There are of course differences in the magnitude, but the structure of the wave patterns of the are quite consistent in both the cases, and also for example, the location of shadow zones and situations like that. So these are quite accurate, and statistically they are quite close to one another. This here goes a bit more details into it and just shows the pure numbers of the acoustic transmission loss, and you can see that they're almost over one another, and the difference is less than 10% for most of the range. There are some discrepancies in the shadow range, but even then this is more of a numerical artifact of the retracing than the method, and even then we are able to predict where are the shadow ranges quite accurately. So this was quite promising, and the results are available in one of these papers, and I have all the data sets for training and testing on my GitHub site. The second scenario that we have tested is not so much into far field or prediction of transmission loss, but more about temporal evolution of the acoustic scattering, which we had analyzed earlier using high-fidelity computational models. So we wanted to see how well can, let's say, the CRAN perform those predictions instead of the computation fluid dynamic models. So we tested the So we trained the CRAN on the time evolution of this acoustic waves for various different set of C-mount shapes. And then we looked at what is the prediction for out of training cases, right? So what we are doing here, again, is we will feed this CRAN with a bit of, with something similar to initial condition, but for, let's say, for a short time period, and that is L sequence, let's say. And this is what we are feeding the CRAN. And then what we want the CRAN to do, okay, you start from this L sequence and let's see how much long you can predict in time, right? And we can see that up to 5 times the initial bit of the initial time set, we can predict quite accurately. And this is for one case and with high frequency. And then we are again, this is a different situation where again, this is the data set that we are feeding the trained network. And this is what it can predict for the next, for let's say the 5 times the time data set being fed into it. So you can see that the solutions are highly stable here, and the physics of scattering and interference are quite well predicted over most of the domain. There are some, of course, this is what I'm showing is the predictions at intermediate locations, intermediate snapshots over the whole prediction length. And you can see there are some differences here, especially near the boundaries where the results are a bit off. And also there are some differences in this, in the prediction and the ground truth over here. For example, it sort of overpredicts it overpredicts some wavelengths, but overall the results are quite good if I compared even over the whole domain. And this is evident from this mean L2 error. And we can see that the average mean L2 error over 15 out of training cases was less than 10%. And especially with the use of Taken's theorem and time data delayed embedding in the training of the network, that we could see that we could have this type of very slow accruement of errors as we are evolving this prediction. So this shows that results are highly stable. So for example, even we can have some sort of initial error in the prediction, let's say around 6.5%, but doesn't really blow up that quickly. So that leads to highly stabilized results, and we can have this predictions over a long time horizon. So to conclude, we have developed deep neural network models which could provide far field prediction over large ranges of acoustic scattering, and also long time prediction of acoustic scattering due to C-mount boundaries with highly stable predictions over long time horizons. The generalized prediction, we have sort of kept 10% as a threshold, and anything above this, we will say it's inaccurate. But results have been the results have been promising so far, with most cases less than 10% errors. There are some predictions errors on the wave and boundary interactions, but overall the wave speed and interference patterns are quite accurate, which shows that predictions are physically consistent. And of course, we need a lot of future work before we can really need to see how these models scale up to largest to various different applications of underwater acoustics. So yeah, thank you for listening to me. That's all I have for today. And I'll be very happy to answer any questions that you may have.